Okay. Testing, 1, 2. Hello. All right, and you know the drill. So.
Yes, thanks.
All right, so don't ignore security. We heard just before. Our next speaker is going to be remote. It's Julien Vermillard from Sierra Wireless. He couldn't make it, unfortunately, but I think we have a nice setup for the remote presentation. So, Julien, I think you're live, so you can go whenever you want.
Okay, thank you. Hello, thank you for joining this presentation, which is about IoT security. So when I say IoT security, I mean security of your application, your cloud service. I'm not going to talk about privacy. I'm going to talk more about how to create a secure applications. So first, who am I? I'm software engineer at Sierra Wireless. I'm working on a cloud service. It's called Advantage.net. It's for managing and creating application around Sierra Wireless gateways and modems. I'm also involved in Eclipse IoT, so I'm project lead for Leshan and also committer on Wakama in California. So if you want to reach me, you have my email and my Twitter handle. So first, a little agenda. So a little introduction about why IoT security have so many news coverage, and then some stuff to secure, from hardware to cloud security, from the device communication until your real application server. And at the end, I will finish with a different open source project at Eclipse IoT for building a secure IoT infrastructure. So first, yes, as you can see in the news, there is a lot of coverage about IoT security. Some articles are already clickbait, but some are really interesting. For example, there is a lot of concern about the connected home and the connected car because, well, because we are connecting the physical world with the cyber world, and we now have a problem with the cyber security because it's having a great impact on the physical world. The typical example is the connected car. If I connect a car with all the electronic devices connected to the CAN bus, and the CAN bus connected to a modem or a Wi-Fi module connected to the internet, what about the physical security of my car? So yes, there is a lot of concern, but it's a real concern. If you look at this study from HP45 from last year, they reviewed a few popular devices, mainly around home automation, like smart TV, door locks, well, very classical home automation devices. So 90% collected personal data. So, well, this is not a big surprise, because when your smart TV is connected to a cloud service, there is a good chance they're collecting personal data, or your door locks is a very personal object. So yes, it's not a big surprise. What is the big surprise is 70% use encrypted network services, basically no encryption on the service. So, well, this one is really wrong, and you will understand later why it's like that. So the first thing to do when you are building an IoT application, it's taking care of the hardware security. This one is not so obvious, especially if you're more server or cloud developer. You say, okay, why I need to protect my hardware from physical access? What's the problem? If someone tamper one device, it's going just to tamper one device. Well, here the real risk is backdoors and rogue firmware. Basically, if you look at this presentation from Blackout about the smart Nest thermostat, well, it's not only in the Nest thermostat. A lot of devices are vulnerable to this kind of attacks. You can just get an object, install a rogue firmware, and with a backdoor, and just, I don't know, bring it back to the shop or sell it on eBay, and you have a nice backdoor inside someone's house. So yes, depending on the application, can be a concern. So now we have nice hardware platform with different way to mitigate these problems. The main one is a secure boot. The secure boot protects the hardware from booting firmware, not from the vendor, which is solving the problem, but creating other problem like a great vendor lock between the hardware platform and the software, and which can be a concern. For example, in the home router space, we have a lot of custom firmware and nice open source solution. And with this secure boot, you are securing your hardware, but you are also creating a great lock and preventing open source implementations. The next element, once you have a running hardware platform with basic security feature, it's how do you upgrade your software. You are going to create an object and send it to your customer. It's going to live maybe for 3, 4 years, 5 years, or maybe 10 or 20 years if it's an industrial application. So software is, well, what is it? Is software is if you add security on top of software, you are going to have some problem at some point, maybe broken algorithm or security fault in one of your components. So you need to be ready to upgrade your devices, and you need to be ready to do it over the air. Basically, you need to be sure you are able to push a security fix or a new security feature as soon as possible without asking, but you need to be ready to do it as soon as possible and push it over the air. So this feature is not so easy to do. It's complex, and you have a cost on your hardware. The main complexity is the custom bootloader, and the main cost for your bill of material is the flash size. For example, this is a strategy for upgrading a device. You have a bootloader, you boot a partition, maybe the firmware V1, and while firmware V1 is running, you can receive an upgrade for firmware V2. You flash the firmware V2 in the second partition. Once everything is fine, you have checked the integrity of your firmware. You say to the bootloader to boot on the firmware V2, and then you reboot the bootloader, boot on firmware V2, and next upgrade, for example, for firmware V3, will go to the previous partition, the one for firmware V1. You can also add some nice feature like automatic fallback. In case, for example, the firmware V2 is not running correctly, the bootloader can fall back to firmware V1. This one is not so difficult to implement, but as you see, you need twice the flash size, and twice the flash size is a cost, and is also a cost for power consumption. Another option is to create a patch, a binary patch for patching the firmware. So you run the firmware, and you have a small partition for installing the patch. So what you do is you download the patch, write it on the flash partition, and then the bootloader, while rebooting, will apply the patch. So you need to be sure you're able to apply the patch, and to be if you have a power loss during the patching, you need to be able to resume in the middle of the firmware patching. And if you want to create a compact patch, it can be complex depending of your architecture. If it's a small microcontroller, you can do a nice bytecode patch. But if it's a Linux platform, you need to create maybe a bytecode patch for the kernel, but also a file system patch, which is different for the root file system. So creating a patch-based system is a bit more complex. And yes, you need to be bulletproof, because upgrading can be complex. And yes, for example, Flash are sometimes really difficult to upgrade. For example, if you use a Raspberry Pi with a SD card, you can see you can have unexpected problems with Flash, or unexpected power loss during the flashing. You need to be resistant to that. You need to be able to resume your download, your firmware download, due to network errors, especially if you are using wireless connectivity. And maybe you need to be able to fall back in case of unexpected incompatibilities, because you are shipping devices overseas or to any customer with maybe a different hardware configuration than the other one, and maybe you are not able to test everything, so you need to maybe to have a fallback mechanism for going back to the previous version. And you need to be able to check the integrity with a checksum or a cryptographic signature for checking the origin. Why you need to be bulletproof? First, because if you have, even with a low failure rate, if you are going to break 1,000 devices, well, if it's truck or plane or car or home automation system, you need to ask your customer to send back the devices. So yes, so it can be a problem. Yes, for example, for trucks, you don't want maybe to send 100 trucks back to the garage. So once you have a secure way to upgrade your device and a secure hardware platform, you want to have a secure communication, because yes, without secure communication, you are not going to have any privacy, or you have no authentication between the device and the server. So for building secure communication today, we don't have a lot of protocols. Basically, TLS, the new name for SSL, and DTLS, the TLS version of datagram. And also we have more VPN infrastructure technology like IPSEC. We don't have today a specific standard for IoT, because security experts are not fun to create about creating a new standard, especially for IoT. So yes, we need to use TLS and maybe some specific Cipher suit for TLS for IoT. So yes, for example, you can use a pre-shared key mechanism. So pre-shared key is basically sharing a common secret between the device and the server. So for example, it's like your Wi-Fi access point. You know the secret. The access point knows the secret. So you are able to do a secure handshake and make mutual authentications. Well, there is some limitation to this security scheme, but it's fitting on small devices. It's not really cheap. For example, I'm not talking about CPU usage, but here, if you can see the RAM usage, memory usage, it's not fitting in Arduino Uno, for example, but you can use it on 32 bits microcontroller. It's running, and since now we have more and more hardware accelerator, it's not that difficult to run it on constrained device. But if you have more power, more CPU power, maybe you can use elliptic curve private public key cryptography. So maybe you can have forward secrecy. So forward secrecy is a way to negotiate an ephemeral secret for every new session. So if someone managed to get the private keys, the long-term secret of your device, they are not able to decrypt the past communications. And what is nice about public keys is you don't need to share a private secret like a PSK, so you just need to know the public key of the remote peer. So this is a more robust Cipher suit, but it's more complex, it's more RAM, it's more CPU. Mainly CPU, DFLMAN and DSA are not so easy to implement in microcontroller. And if you have even more CPU power, maybe you can use certificates. The certificate is what we use for authenticating HTTPS server. So in place of knowing the public key in your database of the device, you just delegate the validation to a chain of trust. So if a device come and connect to your server with a valid certificate, even if you don't know him previously, you can just trust him and connect with him. But if you use certificate, you are going to need to pass the certificate. You are going to manage revocation. Certificate have the end of validation period. So if you want to check the validity of the certificate, you need to check the date. So for checking the date, you need to have the time. So you need to have a real-time clock. Maybe you need to synchronize the real-time clock using MTP. But MTP is not so secure, so you have a kind of chicken-egg problem. And yes, it's basically more complexity on your device, checking revocation, so more protocol like OCSP or DTLS. OCSP stapling. You need also to take decision about I am going to hard fail or soft fail if I'm not able to check the validated of a certificate. So yes, so you need to make a choice. Maybe it's mainly a problem of infrastructure and also a complexity on your device. PSK, pre-shard key infrastructure, is very simple. Everybody can understand that, but is weaker. And yes, certificate infrastructure, what we call PKI, are complex, but you can maybe use a third-party provider. So once you have the secure communication, you need key distribution. You need to distribute your secret. Have different credential for different devices. You are not going to use the same password for every device. So yes, so maybe you are going to generate a different password at factory for every device. Are you trusting your factory? Do you need to move big plain text list of credentials from your factory back to your server? Maybe you can try with, well, this is not a really good example, but people try to generate a password from the serial number of a mobile phone, the email, for example, with a common secret for the whole fleet. So it's nice because it generates automatically a new different password for every device. But if someone gets not so secret, is able to access the whole fleet. So yes, you are going to put a secret, an initial secret at the factory, but yes, you need to be able to change it. And yes, of course, don't wait the first security problem for doing that. So a good practice is to change the secret directly during the first communication and change it often during the life of the device, so you are always sure in case of any problem, you are able to rekey your whole fleet of devices. So how to do that? Maybe you can use an enterprise PKI protocol like CMP, Certificate Management Protocol, if I remember correctly. Or for PSK or certificate, we have a new standard for doing that, which is part of Lightweight M2M, which is called the Bootstrap. So how it's working, you can flash the credential inside your device at the factory, and when you are shipping your device, the device just has the Bootstrap credential. It can't reach the final server. So the device connects to the Bootstrap server. The Bootstrap server writes the final credential, and then the device is able to connect to the device management server, and the device management server is able to start managing the device. So it's great that any time you can rebootstrap the device by triggering a bootstrap. So you are able to change over the key. The last element to secure is your server. So why you need to secure the server more than any cloud applications is first if you connect a large fleet of device to a server or a cloud platform, it's going to be a joystick target. Because, for example, if you are managing, I don't know, home automation device, it's meaning you can control a lot of devices inside the home with nice connectivity. So it can be a great botnet for spam or attacking another targets. So, well, mitigations, well, it's basically creating a secure cloud application and maybe explain to your user you stronger authentication feature like two-factor authentication. Something interesting also is just to collect the minimal data. For example, if you have an application and you want an embedded application, maybe what you want to do is to get automatically memory dump of the device back to the server. You need to be careful because when you are just memory dumping your device, maybe you are going to get a secret or not so essential data for you, but which can be exploited by someone breaking into your server. And also, a good solution is to isolate as much as possible the web interface, the end user graphical interface with the device communications. So yes, so a lot of subject to take care. Where do you start? So maybe you can ask more time or more budget to your product management team. And yes, good chance they are going to answer they don't care and they want you to ship the product. So, well, this is not really a good situation, and now you are part of 70% unencrypted network services. Yes, so what you can do, well, if you don't have time or budget for that, maybe you can take a solution for a vendor. Few vendors have a nice stack from device to the cloud service, security, and all the correct elements for securing your applications. But you can also look at Eclipse IoT solutions. So yes, what we are doing, some project for Eclipse IoT is to try to fix and to provide solutions for these different project problems. For example, the first one is the Eclipse Leshan. So Leshan is basically a Lightweight M2M implementation in Java for building device management server, Bootstrap. It's supporting DTLS, PSK, and public key mode for communication, certificate are coming. But also there is a client for building for stronger devices, devices able to run Java. So if you take Leshan, you're able to build a Bootstrap for distributing key, a Bootstrap server. and also a device management server. So with the device management server, you are able to update your firmware, update your software. There is a standard inside Lightweight M2M for installing and upgrading software. You can manage your secrets, you can monitor and configure your device, and also you can build your application. If you build your application inside Leshan using Lightweight M2M, automatically you are using the DTLS communication and all the secure communication facilities. You can also use IPSO object if you want to create standard object for your application. Wakama is a bit the counterpart of Leshan, but is in C, so it's more focused on the side. There is a client, so server. You can bring your own IP stack, so it's great for building an embedded application. So you can use it on whatever operating system or even on microcontroller without any operating system. And you need also to bring your own DTLS implementation, so you can use TinyDTLS, OpenSSL, whatever you want. And yes, the Bootstrap is supported well. It's under review, it's inside a pull request, but it's going to land in Wakama master. So once you have Wakama, what you can do, receive upgrade package from firmware or software, but you still need to implement the live over-the-air flashing of your platform. So it's really hardware dependent, so you need to do that. And you can run it on Wakama. It's running on Linux. It's really easy to run it on Linux or embedded Linux. But it's also running on Arduino Mega. But without security, Arduino is not powerful enough to do that without DTLS. But on ARM Cortex processor like M3, you can run it with this wall security feature. There is also a new project called TinyDTLS. So TinyDTLS, there is a new proposal for moving it to Eclipse. So it's a DTLS implementation in C especially for embedded system. It's very compact. You can use it, of course, with Wakama. And you have nice example for running it on Linux and Quantic OS. But you can use it on other operating systems. You just need to hack a little support for removing some modify. If def Linux, change the core with your system call. It's really easy to port to new targets. It's supporting different Cipher suites like the PSK I presented earlier, and also the elliptic curve cryptography for doing public key private cryptography, perfect forward secrecy. So yes, as you can see, for security, we at Eclipse IoT, we have a nice toolbox with different elements for building a secure cloud service, with a nice device management facility for sending upgrades, configuring your device, and you have everything inside for inside the device, from microcontroller to larger Xbox for receiving upgrade, receiving key, and creating a secure IoT device. But today it's really different project with it's really a toolbox. You need to get the different tools and make the whole integration yourself and create the hubs. So now what we are trying to do is to create something more integrated, creating more integration between the different projects, between TinyDTLS, Wakama, and Leshan, providing example. For example, I'm working on an embed example on how to run TinyDTLS and Wakama on the ARM Cortex M3. There is also some portage to Arduino to be open sourced. There is a lot of effort. People who already adopted Wakama and Leshan to provide a very nice documentation and ready to use implementation, so everybody can easily build secure IoT application, and so we can make it easier for stop building non-secure IoT applications. So thank you. Wow, I'm just in time. Perfect. If you want to contact me, my Twitter handle, my email. Yes, and I'm going to take questions. I don't know how exactly, but yes, Benjamin, can you handle that?
I can be the proxy. Are there any questions for Julien? There are not, actually, as far as I can see.
Okay. So thank you, and have fun at EclipseCon.
Thank you very much, Julien, and good night, I guess.
Yeah,
Thanks for staying up late.